Right, let's go through this exercise then. As we said, we wanted you to go through the 11-step guide. Step 1, determine the design objectives. Now, this is specified in the question. This is property protection, and therefore the ventilation system must ensure that a clear layer height is maintained 0.5 metres above the stock. So that was step 1, that's the design objective. Step 2, we need to determine the design fire size to be adopted. Now, the formula to determine the fire size is as follows. As again, you've got QP equals chi times the area of the fire times the heat release rate density. If you put in the variables, you should have got this. QP equals 0.67. Don't forget that's default value of chi. That's the convective heat output of most typical fires. And you times that by 9, which is the area of the fire, 9 square metres, and you've got your 425. That should give you an answer of 2563. So that is the design fire size that we're going to be basing our smoke control system on. Let's move on to step 3 now. Step 3 is determining the mass flow rate of the smoke. Now again, we firstly need to establish whether this is classified as a simple plume or a complex plume. Now in this case, the design fire is located in the reservoir where it's going to be extracted, so it's a simple plume. Now we have to decide which model to apply. Is it a line plume, is it a corner plume, wall plume or an axisymmetric plume? Well, as the stores are going to be located everywhere, we have to look at worst case, and the worst case is the one that will give you the worst mass flow rate, which is an axisymmetric plume. In other words, in the centre, because it's got air coming in from all angles. So the model we're going to apply is the axisymmetric plume. Now next we have to decide whether it's a near field or a far field model. Don't forget, if the clear layer height is greater than the longest dimension of the source multiplied by 5, then it will deem to be a far field model, not a near one. If it's not, it's a near one. That's the parameters. Now in this case, 5 times the longest dimension of the source, and it's assumed to be a 3 metre by 3 metre fire, is 5 times 3, which is 15. And the clear layer height is only 5.5. Clearly, it's a near field model. So we know that we're looking at the near field axisymmetric model. So this is the model we have to apply here. M equals CE P times Z to the power of 1.5. Like I say, where M is the mass flow rate of smoke in kilograms a second. CE is the coefficient of entrainment. P is the perimeter of the source. Don't forget the perimeter. And Z is the clear layer height in metres. Now, in this case, we need to establish which coefficient to apply. Again, if the clear layer height is greater than 3 times the longest dimension of that source, you use 0.19 as the coefficient. If not, you apply 0.21. Now, in this case, 3 times 3 is 9 metres. Clearly, this is greater than the clear layer height. Therefore, you apply 0.21 as the coefficient. So this is 0.21 to apply. Put in known variables. You put them in, you get this. M equals 0.21 times the perimeter, which is 3 plus 3 plus 3 plus 3. So this is the perimeter, equals 12. That is times 5.5 to the power of 1.5, which gives you 32.5 kilograms a second. So the mass flow rate beneath the plume is 32.5 kilograms a second. So we know how much smoke's been produced, but how hot's it going to be? Step 4, determining the temperature of the smoke. Now, to determine the temperature of the smoke, again, we use the following formula. Theta equals QP divided by MC, where theta is the increase in temperature, QP is the convective heat output, M is the mass flow rate of smoke, and C is the specific heat capacity of the smoke. Put these values in, we've got these values. Theta equals 2563 divided by 32.5 times 1.01. Your theta value, your increase in your temperature of the average temperature of that smoke is 78 degrees Kelvin. 78 degrees Kelvin, that's the temperature increase. This gives us the increase in average temperature. However, we want to know what the absolute temperature is. In other words, how actually hot is that smoke? And again, you use this formula. TL, which is the absolute average temperature of the whole smoke layer, equals TO, which is the ambient temperature of the air, plus theta, which is your obviously increase. And it gives us a TL value of 366 degrees Kelvin. That's how hot the smoke is. Now we know how much smoke we have and how hot the smoke is. We now need to start determining how we're going to extract this smoke. Before determining this, we have to consider stratification, and this is considered in step 5. Now in this building, due to having such a low clear layer height, so low, stratification will never occur. It's too low. So in other words, although you've got to look at it, you don't have to apply it. In this particular case, you can ignore it. You go straight on to step 6. Step 6, determining the ventilation requirements. Now you've got a couple of choices. You can either have natural ventilation or mechanical ventilation. And again, generally natural ventilation is preferred. Basically, a lot of it's on cost implications. But if it's not possible, if there's any issues why you can't have natural, then you might have to go for mechanical. So let's progress on the assumption that natural ventilation is going to be installed in this building. The first thing is to determine is the number of reservoirs that you're going to have in your building. You need to determine, first of all, how many reservoirs. Now, again, for cost reasons, you would like to have the minimum that meets the design criteria. You don't want to put reservoirs in for no reason. The limit to the size of a compartment, a reservoir, in a natural ventilation system is 2,000 square metres. So let's look at our warehouse. The building is 100 metres by 40 metres. And again, the maximum size of reservoir is 2,000 square metres, as we said. So clearly, as you can see, we can get away here with 2 reservoirs. 50 by 40, which gives you both for 2,000 square metres. Based on that design, that's what you'd have, 2 reservoirs. Now we know how many reservoirs we're going to get. We need to know what area of ventilation is required in each reservoir. We need to work out the factor called the AVCV factor. And to determine the AVCV factor, in other words, the area of vents in each reservoir, this is the formula to apply here. This formula here, where M is your mass flow rate of smoke, you've got your rho density of air, ambient air, your TL is your absolute temperature of smoke layer. Don't forget your AV, CV, AICI is the ratio of outlet to inlet. In this case, because only 2 reservoirs, it's 1 to 1. In other words, there's 1 going out and there's 1 bringing the air back in again, so it's 1 to 1. TO is the temperature of ambient air, and again taken here as 288. G is 9.81. The depth of the smoke layer in this case is 2.5 metres. And we've worked out your theta, which is your temperature rise of the smoke layer. If you put them into your formula as you should have done, this is what you should have got here. And if you work that out, it comes out as AVCV equals 12.621. 12.621. So we need at least 12.621 of aerodynamic area for each reservoir. That's what we need. Now that completes that step. So that's what you need to work out, the aerodynamic area. We'll move it on later on. Let's move on to step 7, which is determining the number of ventilators now. Well, we know the total area of ventilation is required, which is 12.62. Now, this is aerodynamic free area. As I said before, we need to now work out the coefficient of the ventilator. In other words, how efficient will that ventilator be? And again, generally, it's 0.6. Now, if it's different, you'd obviously use a different factor in the calculation. In this case, generally 0.6, it was 60% efficient. So you divide 12.62 by your 0.6, which means you need about 21 square metres of geometric area. So that's the actual size, 21 square metres of actual ventilation area in each reservoir. Now, don't forget, ventilators don't come bigger than 6.25 metres. So we need at least 21 divided by 6.25. We need at least 3.36. Obviously, you've got to round it up. We need at least 4 ventilators. So we need at least 4. That's absolute minimum ventilators to achieve our aerodynamic and geometric area. That's what we need. That's the absolute minimum. Now we need to know, where do we locate them? So where are we going to put our ventilators? Now don't forget, before you carry this out, you've got to check the next step, step 8, which is the stagnation check. And again, it only applies to natural ventilation, and it means that ventilators cannot be more than 10 metres from the side of a room and no more than 20 metres apart. And this is because the smoke, again, may stagnate in between them. So this is for natural ventilation, not mechanical. You carry out a stagnation check. So if we look at our reservoir here, 50 metres by 40 metres and mark a line 10 metres on each angle and make sure it's not 20 metres apart. Do you see what you're doing? You're making sure that on there's some ventilators. You can't be any further apart than that. And this here shows us that we need to install the ventilators where we need to install them to prevent stagnation. As you can see, although we determined earlier we only needed 4 ventilators to meet the geometric area, we actually need 6 now minimum to meet the stagnation check. So as you see, that's an overriding factor here. As you can see on here, 6. We have to, because you can't have more than 20 metres apart. So we need 6 ventilators with a total aerodynamic area free of 12.62 square metres. That is what we've just determined by doing that. And that covers step 8. Let's move on to step 9. Now this is the plug hole in check. Now again, this applies to both natural and mechanical. You've got to make sure that the ventilators won't plug hole and create a vortex, drawing more air, not be efficient and not get out enough smoke. That's what you're trying to work out now. Now don't forget again, there's 2 models to determine if plug holing will occur, and this depends on where the ventilators are located. There's one where the ventilators are located within 2 metres and there's one when it's more than 2 metres. Now, in this case, the ventilators are more than 2 metres away from the edge, and this is the formula we apply now. This is the MCRIT formula to work out the plug holing check. And again, this is where MCRIT is the maximum rate that it can be extracted without plug holing. Rho 0 is the ambient density. G, 9.81, acceleration due to gravity. TO is the ambient temperature. Theta is the increase in temperature. D is your smoke layer depth. And don't forget the new parameter, WV. We've got to work out the WV, which is the width of a ventilator of a circle which would cover the same area as a normal, any shaped ventilator. So WV, you've got to work out your WV, and you use this formula. Now, we did determine earlier that we needed approximately 21 square metres of geometric area. Now, if we divide this by the number of ventilators, it gives us 3.5, doesn't it? So we need 3.5 square metre, that's the ventilator, that's the geometric area. We've converted it with a 0.6, that's the geometric area. So if you could put this straight in the formula, because this is geometric area, WV equals square root of 4 times 3.5 divided by pi gives you 2.11. So our ventilators will have the area, the diameter of a circle, which is the same geometric area as our ventilators, is 2.11 metres. Now we've got all the variables, you can insert them in the plug holing formula, and it gives us this. So you should have had this formula here. Can you see the formula, the parameters put in there? Now, if you multiply that out, you will get an MCRIT of 28.57 kilograms a second. So we know that the critical exhaust rate is 28.57. If we're extracting more than that in each ventilator, plug holing will occur. Now, we need to ensure that the actual smoke leaving each ventilator does not exceed this, obviously. Now, the amount of smoke that leaves each ventilator is your total amount divided by the number of vents. Well, in the amount leaving all the vents, we worked out the M, the mass flow rate, as 32.5 kilograms a second. We know there's 6 ventilators, so we divide it by 6, we get 5.42. Well, 5.42 is much less than the critical exhaust rate, so in this case, we are confident that no plug holing will occur. Plug holing will not occur in this situation. So we've got 6 vents, each with an aerodynamic area of 2.1 or a geometric area of 3.5, located as shown on here, will be satisfactory in this case. That's the final answer to this. And that covers step 9. Now, step 10 is to check the air inlet velocity, if necessary. Again, this is a natural ventilation system, so this does not kick in, and all the air is going to come in from the reservoir anyway. So this does not apply in this particular case. It's natural ventilation. So again, you can skip step 10. The final check, which does apply here because it's natural ventilation, you need to carry out post-design conditions. You need to consider weather conditions, make sure there's no adverse effects on the ventilators due to where they're located. They're not located at an angle of more than 30 degrees. If you are, you've got some precautions in place. And also look at other tall buildings in the area to make sure you're not going to get a positive pressure. In other words, it's not going to be effective. If you've got a building right next to yours, a tall building, you might not get away with natural ventilators. That completes this exercise.